Dr. Dayana Mathew is a marine chemist and R&D specialist with a Ph.D. in marine chemistry and a master's degree in hydrochemistry. She has extensive experience in marine science, geochemistry, and environmental monitoring. She completed her Ph.D. research at the CSIR National Institute of Oceanography, India, and served as a consultant at the UNESCAP in Bangkok, contributing to ocean-focused climate action.
Hello everyone, I'm Dayana Mathew, and I will be presenting about harnessing ocean climate synergies in a perspective of climate change mitigation and adaptation. So here is the outline of contents covering in the presentation. I'll be talking about ocean climate nexus, ocean acidification, impact of ocean warming, and finally, ocean-based mitigation and adaptation strategies. As we all know, climate change is the long-term shift in climate driven by human-induced greenhouse gas emissions. Carbon dioxide contributes to 3/4 of these emissions, followed by methane and nitrous oxide. So all these greenhouse gases trap heat radiation and disrupt global weather. Along with the increase in temperature, extreme weather events are becoming more frequent and intense. Climate change is a reality we all face these days, but it's a grave danger for our future generations because today's emission will affect future for decades to centuries. So International Panel on Climate Change, IPCC, reported the necessity to limit global temperature increase below 1.5 degrees Celsius. And in 2023, the increase in temperature was 1.1 degrees Celsius above pre-industrial time. However, in 2024, we already surpassed this threshold, and World Health Organization confirmed that 2024 was the warmest year on record with 1.55 degrees Celsius above pre-industrial time. The root cause of this increase is fossil fuel emission, along with temperature increase due to alterations in ocean and atmospheric pattern happened due to an intense El Nino event. So surpassing 1.5 degrees Celsius threshold in a single year it is not like permanent exceedance of Paris Agreement target, but it serves as a critical warning. The current mean carbon dioxide concentration in the atmosphere is 427.09 ppm, which is 52% increase from pre-industrial time. In pre-industrial time, the value was 280 ppm. So to limit warming at 2 degrees Celsius, atmospheric concentration should remain less than 450 ppm. So let's see the relationship between emission levels and temperature rise. So this is a graph from IPCC report 2019. And on the x-axis, it's cumulative carbon dioxide emissions since 1850. And y-axis shows increase in temperature. Cumulative carbon dioxide emission refer specifically to total carbon dioxide emitted by human activities over time. So this metric is crucial because historic increase in surface temperature directly correlates with the increase in carbon dioxide emission in the post-industrial time. So this clear relationship allows models to predict future temperature increase depending on different scenarios for future carbon emission levels. So there are 5 different scenarios predicted, and I'm talking about like scenario SSP 1 to 1.9. So SSP stands for Shared Socioeconomic Pathway, and this 1 to 1.9 scenario, it reflects more closely a 1.5 target under Paris Agreement. The other scenario, SSP 1 to 2.6, represent scenario to limit warming below 2 degrees Celsius. And I'm talking about the extreme case, SSP 5 to 8.5, which represents a scenario with high GHG emissions. So all these scenarios, it helps us to determine how much warming we will experience within 2050. And the lever is somewhat in our hands because every ton of carbon dioxide emission adds to global warming. So we know that carbon dioxide concentration in the atmosphere is very high, and it is going to stay in the atmosphere for hundreds to thousands of years until it gets absorbed by natural things. So let's see ocean role as a carbon sink. The ocean plays a crucial role in climate regulation due to its immense carbon storage capacity, and it holds 60 times more carbon dioxide than atmosphere. So every year, ocean absorbs 30% of anthropogenic carbon dioxide emissions. Another 30% will be absorbed by terrestrial ecosystems, which includes forests, green grasslands, and soil together. So 60% of anthropogenic carbon dioxide emission will be absorbed by natural systems. Remaining 40% stays in the atmosphere, driving global warming and climate change. So in addition to carbon dioxide absorption, ocean absorbs 90% of heat added to the climate and also regulates weather and climate systems. However, continued emission overwhelms these carbon sinks, leading to ocean acidification, biodiversity loss, and climate instabilities. So let's talk about ocean acidification. So ocean surface water pH, it has been observed to be declining by 0.017 to 0.027 units per decade since 1980s in response to carbon dioxide absorption. As more carbon dioxide enters the ocean, it reacts with water and increases hydrogen ion concentration in water, thereby decreasing ocean pH. The absorbed carbon dioxide disturbs the balance between carbonate species, with the concentration of dissolved carbon dioxide and bicarbonate increasing and carbonate decreasing, resulting in less precipitation and dissolution of calcium carbonate species. Calcium carbonate. So this affects calcifying organisms such as coccolithophorus, sea butterflies, and many more carbonate-shelled organisms. Corals are also made of less crystalline calcium carbonate, and they're very sensitive to acidification. The current average ocean pH is 8.1. The drop of pH from 8.1 to 7.75, as projected under high emission scenario like SSP 5 to 8.5, will cause major shifts in marine ecosystems and food web, including loss of most coral reefs globally. So as the ocean warms, temperature increases, right? So on average, this increase is 0.71 degrees Celsius from 19th century. That's the current increase, 0.71 degrees Celsius from pre-industrial time. So the sea surface temperature is projected to increase up to 0.85 degrees Celsius in the scenario SSP 1 to 2.6 and up to 2.82 degrees Celsius in the high emission scenario. Warming leads to sea level rise because 1/3 of this ocean water, 1/3 of this contribution is from the warming and the expansion of the ocean water, whereas accelerated melting of glaciers and ice sheets contributes to 2/3 of sea level rise. So the sea level rise already increased by 0.24 meter with an average rate of 3.2 millimeter per year. And warming increases heat wave anomalies and thereby results in bleaching of coral reefs and increased fish migration. And also it increases extreme weather events. So let's see how ocean warming affects the coastal communities or low-lying communities. So the rising sea level poses direct threat to coastal regions in developed and developing countries, as well as low-lying coastal zones and small island developing states, which is less than 10 meters above sea level. Millions of people living along these coastal fringe are under imminent threat of sea level rise. So 25 centimeter of sea level rise might not sound dramatic, but it leads to more intense and severe flooding and frequent damage of coastal infrastructure and more intense seawater intrusion. Low-lying areas are already experiencing chronic flooding. So over time, these areas may become uninhabitable. So there is a map of village from Solomon Island. It's Nusa Banga village. And this sea level rise indentation map shows its current coastline with this blue line, but the yellow line shows zero point 0.5 meter contour, whereas 1 meter contour you can see in this picture. So as sea level rise, it affects the coastal communities and it changes the area available for communities to live and disrupts coastal ecosystems. So another impact of warming is increased heat wave events. Heat wave is actually marine heat wave event is existence of prolonged enormously warm waters. It occurs during hot, dry, and windless condition that makes it impossible for hot water in the upper layers of the ocean to get mixed with cool water below. So more intense heat wave events are reported in this century, especially like a very intense heat wave event occurred during 2016. So pictures on the right hand side shows fish mortality in the southwest coast of Fiji with intensity of plus 2.8 degrees Celsius heat wave. So must note that this temperature is the average sea surface temperature predicted for high emission scenario. So marine heat waves are also getting intense in the subsurface waters. Normally, heat wave events occurs in the surface layer, but reports says that marine heat waves are getting more intense in the subsurface layers as well. So there is plus 5.2 degrees Celsius increase reported at 150-meter depth. So the consequences of heat waves include disturbed ecosystem structures, reduced biological productivity, fish mortality and migration, economic loss, and coral bleaching. Here is the picture of coral bleaching occurred in Northeast Australia. So, ocean warming leads to bleaching of corals. Actually, bleaching happens when environmental stress, like temperature, kills algae symbiotes in the coral host, revealing the coral's underlying white skeleton. It's shown in this picture. Being the prominent marine ecosystem with highest level of biodiversity, coral bleaching affects biodiversity and livelihood of people who depends on it. Warm water corals. Warm water corals are corals present in shallow depths, and they are at imminent threat of this warming. So they can thrive at a temperature between 23 to 29 degrees Celsius, but exceeding the limit for long, that causes their bleaching. So this picture shows extreme bleaching occurred in 2016, and the picture on the right hand side shows the bleaching of even the largest and oldest coral in Great Barrier Reef. So let's see the impact of warming in coastal ecosystems and biodiversity in general. So this graph is also from IPCC report 2019. And here the vertical axis on the left-hand side shows global mean surface temperature. And on right-hand side, it shows sea surface temperature increase. And there are color indication shows the risk levels. In fact, increasing average water temperature reduced the tolerance of marine ecosystems to local temperature rises. So record high sea surface temperature weakens carbon uptake and it disrupts the marine ecosystem. So here you can see that kelp forests and seagrass meadows are kind of already in moderate risk, and warm water corals are already in like high risk of warming. So let's see how we can solve this issue. So let's discuss some of the mitigation strategies based on ocean solutions. So actually mitigation focuses on addressing the root cause, such as protecting natural carbon sinks, transitioning to renewable energy, and reducing greenhouse gas emissions. So to protect carbon sinks, conservation and restoration of blue carbon ecosystems, such as mangroves, seagrasses, and salt marshes are essential. Carbon sequestration and storage by blue carbon ecosystems have been identified as a powerful natural solution in the fight of climate change. So they can sequester and store carbon up to 4 times more effectively than terrestrial ecosystems, and they store carbon in the sediments for millennia. So storing carbon or sequestering carbon is a solution. It's a mitigation strategy to reduce atmospheric carbon dioxide. So, in Spotlight, we have Indonesia's mangrove revival. About 0.6 million hectares were under restoration through community led initiatives in Indonesia. Let's see another mitigation strategy, and that's offshore renewable energy. It has crucial part of to clean energy transition, supporting mitigation goals of reduced carbon dioxide emission and energy security. Offshore wind offers vast clean energy potential with strong, consistent output and minimal land use. Here on Spotlight is North Sea's offshore wind farm, powers millions of homes, and it is co-located with marine aquaculture. So it has multi benefits, and it's powering millions of homes with clean energy. Another mitigation strategy consider is decarbonizing ocean-based transport. It's a critical sector for achieving Paris Agreement targets, as emission could rise up to 50% by 2050. Emerging solutions like hydrogen fuel, onboard hydrogen storage, or other energy efficient improvements are key to decarbonize the shipping sector. Let's see some of these adaptation strategies to strengthening ocean resilience. To adapt, we must enhance the ocean's resilience through nature based solution and infrastructure innovation. Coral reefs and blue carbon ecosystems protect coastlines from erosion, sea level rise, and storms. In addition, they support biodiversity and livelihood. So, developing smart coastal infrastructure, such as living shorelines and floating breakwaters, are beneficial to reduce vulnerability. In Spotlight is the Maldives coral gardening. Coral gardening is actually restoring the degraded reefs by collecting healthy coral fragments, growing them in underwater nurseries, and then translating them to damaged reef areas to regenerate coral cover and support reef resilience. Then another strategy is climate resilient fisheries, because ecosystem based fishery management prioritizes ecological health and sustainable harvest levels. So they help to maintain food security, livelihoods, and ecosystem stability as ocean conditions change. By adapting to shifting species and supporting alternative incomes, communities can better withstand climate shocks. For example, in this picture, there is aquaculture along with ecotourism. So, diversification supports coastal communities with alternative income sources to reduce the pressure on fisheries. Another strategy is data driven early warning systems. They're essential for adaptation because they provide timely, accurate information to help coastal communities to prepare for extreme events. Technology integrated early warning systems improves coastal preparedness and disaster response. and thereby reducing mortalities and coastal disruption. Similarly, policies and international frameworks are equally crucial. They ensure coordinated cross sectional approaches that link ocean health, climate resilience, and sustainable development. So, to conclude, ocean is both the victim and solution in the face of climate change. While it continues to absorb carbon and heat, growing stresses are threatening its ability to protect us. So, to secure a climate resilient future, we must act now by reducing emissions, restoring blue carbon ecosystems, and advancing sustainable ocean use. And also, we need to invest in adaptive solutions. Thank you.